Hello students, today I am going to deliver a lecture on measurement of cyclical variations and random component present in a time series data. This lecture is based on the BSc 6th semester statistics major paper Applied Statistics, which is taught in the colleges under Dibrugarh University. Measurement of cyclical variations. A crude method of measuring cyclical fluctuations CT of a time series YT is provided by the residual method, which essentially consists in eliminating the two components, namely trend TT and the seasonal variation ST, and then removing the random component or irregular variation RT by averaging. Using the multiplicative model YT, which is nothing but TT into ST into RT into CT, the steps involved in the computation of cyclical variation by the residual method are summarized as: calculate the trend value TT by moving average method, and seasonal index, which is to be taken in fractional form and not in percentage form, preferably by a moving average method. Then divide YT by TT into ST as first divide YT by TT to get ST into RT into CT. Then divide ST into RT into CT by ST to get RT into CT. So the moving average of suitable period of these RT into CT values obtained in above steps smoothens out the random component RT, thus leaving the cyclical component CT. So the residual method is the most commonly used method of measuring cyclical variations. Next, the random component in a time series data. There is no formula that can be obtained to measure the random component directly at any given point of the time series. Usually, the non-random components are determined and then random residual, which is left unaccounted for by these components, is obtained. Even this becomes difficult when oscillations appear in the series. The varied difference method enables us to estimate the variance of the random component in a series. Now, the various difference method. Let us suppose that the series can be represented as the sum of functional part and random component as given below. That is, YT is expressed as A0 plus A1t plus A2t square plus AK minus 1 to the into t to the power k minus 1 plus epsilon t. Here epsilon t is the random component. And here epsilons are independently and identically distributed. That expectation of epsilon I equal to 0, covariance of epsilon I, epsilon j equal to 0 for all I is not equal to j, and variance of epsilon I is equal to capital V, that is the constant. It is known that for a polynomial yt of mth degree in t, delta r yt, rth difference equal to 0 when r is greater than m, where delta yt is equal to delta yt plus 1 minus delta yt, where the interval of differencing being unity and delta is the difference operator. Then we proceed with differencing the time series function. The random element becomes more and more predominant until finally the systematic component is completely eliminated. Thus we have delta kyt is equal to delta k epsilon t. As we know that delta is nothing but equivalent to e minus 1, so we can express delta k epsilon t is equal to e minus 1 whole thing raised to the power k into epsilon t. So after expanding e minus 1 to the power k, we have this expression. And from the conditions of expectations and variance, we have expectation of delta k yt is equal to expectation of delta k epsilon t, and which is equal to 0 by the given conditions. From this, we have variance of delta k yt is equal to variance of delta k epsilon t, and which is equal to expectation of delta k epsilon t square, because expectation of delta k epsilon t equal to 0. Then expanding delta for e minus 1, we have this expression, and for the constant variance v, we have, after taking expectation, kc0 square plus kc1 square plus kc2 square plus kck square into. So the sum in the bracket is obtained by comparing the coefficient of x to the power k in both sides of the identity as 1 plus k to the power x into 1 plus x to the 1 plus x to the power k into 1 plus x to the power k equal to 1 plus x to the power twice k. Hence, an estimate of v can be obtained as v cap, that is variance of delta k yt divided by twice k ck, which is equal to mu 2 dash delta k yt divided by twice k ck. Here, mu 2 dash delta k yt is calculated and not the observed variance of delta k yt. Since expectation of delta k yt equal to 0, so hence, once the value of k is known, the variance v can be estimated. So, the variant difference method consists of the following steps. First, we have to prepare this difference table like this. Then, we calculate V1, that is V mu 2 dash into delta yt divided by 2 when k is equal to 1, and V2, that is mu 2 dash delta square yt divided by 4c2 when k is equal to 2. And if V1 and V2 do not differ significantly, then either of them can be regarded as an estimate of V. If they differ significantly, then we have to go for calculating V3, which is equal to mu 2 dash into delta 3 yt divided by 6c3, and which is nothing but mu 2 dash delta q yt divided by 20 when k is equal to 3. So if V2 and V3 do not differ significantly, then any one of them can be taken as estimate of V. Otherwise, we have to go for calculating V4, etc. and proceed similarly till two successive estimates of V are homogeneous. Homogeneity of two successive estimates of V cannot be tested by variance ratio test, that is the F test, because the consecutive terms are not independent. The variant difference method gives the degree of the polynomial with which the trend component of a series can be represented. The only assumption regarding the functional form of the trend is that it must be smooth and not of zigzag nature with small period, since the successive differencing will not eliminate the functional part. So, dear student, I conclude today's lecture here. Thank you.